Okay.
Hi, my name is Jason.
My name is Jorge,
My name is Jesse.
and today we're going to be talking about the Hindmarsh-Rose neuron model. What it models is the spiking and bursting behavior of across the membrane of a firing neuron. The model is represented by three differential equations: dx dt, dy dt, and dz dt. X of dx dt represents the electric potential across the neuron membrane. Dy dt represents the fast ion channels, and dz dt represents the slow ion channels. What we wanted to do with these equations is that we wanted to get them in terms of x of t, y of t, and z of t. So we integrate both sides, and we get x of t, y of t, and z of t. And these are the equations that we're going to use to create our LT SPICE schematics and working analog schematic. We have variables in here: a, which is equal to 2, b, which is equal to 5, r, which is equal to 0.005, s, that is equal to 4, and x sub r, that is equal to -8/5. These were all given to us. And now Jesse is going to be talking about the LT SPICE schematic.
Alright, to simulate this differential equation for the Hindmarsh-Rose, we decided to come up with the design for a integrating circuit. But since the differential equation consists of addition and subtraction, we have to compensate for that by inverting various inputs by using a inverting amplifier with a gain of 1 for the y and for the x squared and x squared. And also for our design we use the LT1633 op amps and the AD633 multipliers. For our design we had to scale the resistance, or pretty much the gain, of the op amps so that when you simulate it we don't have to simulate for a long period of time, because like if we don't scale it, the simulation time is going to take us 16 minutes. So we had to design a circuit to simulate the full differential equation that only simulates within a second.
Cool.
And so this is the LT-SPICE simulation. Then
And the
when we're
circuit?
done, when we're done with the designing the circuit, we built a hard analog circuit with LT-SPICE.
So this is our breadboard model of the Hindmarsh-Rose neuron. And what we have here are 3 LT1630 op amp chips. Each one of them has 2 op amps in them, giving us the right amount that we needed to simulate our circuit. Then we have our AD633 multipliers on this side, which we passed our x signal through to get x squared and x cubed. The multipliers actually have a scaling factor of 1/10, and that was compensated with the resistor values. The op amp here has a capacitor over it, and this is what is actually going to be doing the integrating for us. And once we had this running, we were able to have our oscilloscope model waveforms, and then we also have our LT SPICE schematic simulation.
Alright, for the LT-SPICE simulation, once you run the simulation, we are able to get this output for the X output at 1 volt input pulse. As you can see, for the oscilloscope output, it is quite similar to the LT-SPICE simulation, making a possible circuit. And also, we can also go in depth by changing the input voltage to 2 volts. you can see the spiking increase for the oscilloscope output, the same as the spiking increase for the OptiSplice output. And if we change this to 4 volts, the spiking comes very identical to the oscilloscope output. Also, we can simulate the Y output. There's that, and you can see the similarities of the OptiSplice simulation and the oscilloscope. Like the X output, the spiking for the Y and the Y and the Z varies depending on the output.
That for the Y?
And that's for Z. You see? The curve for the Z at 4 volt output or input. Now for the 2 volts. That's for the Z. You can see that for the LT-Spice simulation at 2 volts for Z, the curves kind of becomes hilly. It's not the defined straight line, the previous one, and that curving is shown in our oscilloscope output too. And for the Y, you can see the similarities. That one
And that's for the Y
at 2 volts.
2 volts. Okay.
And now for the 1 volt. Just change it to 1. Okay. Y at 1. You can see that the outputs are quite identical. See, even with the 2 humps and the spiking for the Y. And then for the Z, see the little humps for the waveform. It's very similar.
Did we get X for 1 volt? Okay.
And that should sum up for our demonstration for the Hindmarsh-Rose circuit. Thank you for watching.
Thank you. That was our neuron model.